In this video, we're discussing measures of location of data. Look, we're going to change our perspective. In the past, we've talked about mean, where's most of your data, where's the center located, and standard deviation, how wild is your data. But those are more global perspectives that says, hey, look, forget about the individual pieces. We're going to summarize everything and really give two numbers to give a good description of the data. That's why they're called descriptive statistics. But what we're interested now is instead, let's look at the individual pieces. How does this one data piece compare on its whole? And we're going to get into the nitty-gritty for each individual piece of data. Let's dive in. Good. So here we go. So one thing that we often think about, and again, all the time you'll read different rankings or leadership boards, and we might see a ranking of something like 92,000 and think, oh my gosh, it's a terrible ranking. I'm not even in the running. But if you consider the whole, again, maybe 2 million people playing this particular game, and that's your ranking, 92,000. Well, if we put things into perspective, again, relatively speaking, then 92,000 out of almost 2 million, that's a fraction of 0.05, rounding to 2 decimals. That means that that ranking, although it might be very long down the list, is actually represents the top 5%. This is a location. It tells you kind of where you are relative to everyone else. This relates to, it's not exactly one-to-one, but it relates to percentiles, and that's our first measure of location of data. The kth percentile, piece of K of a data set, is a number such that, and this is the important part, that K percent of observations are less than or equal to that particular observation, depending on what the actual value is. You can find this percentile. Again, there's a lot of different formulas. It depends on what textbook you're interested in. We'll be using Excel, and so for percentiles, you can simply compute it by using percentile, and there's technically different ones. We'll use this one, INC, which stands for inclusive. Include. That's what the INC stands for. Just a little side note, you'll see just underneath me here, it says exclusive. That's what EXC stands for. This will give you a different answer. Exclusive means that there is no such thing as the 0 percentile or the 100th percentile. And that's what the exclusive stands for. It excludes those opposite ends. And it gives you a little bit of a different calculation therein. So don't use that one. You won't get the right answer. We want to use inclusive, where we can actually talk about 0 percentile and 100 percentile. If I have 0% of values either less than or equal to mine, that represents the minimum, right? That's like the smallest value you can imagine. The 100th percentile represents the maximum, the largest value you can possibly imagine. So that's why we tend to prefer the inclusive, because it's more relative to the position we can identify these. So if we go up to our top 5 percentile that we started with, that represents the 95th percentile. That 95% of values are beneath this ranking. So although 92,000 seems like a terrible ranking on a leadership board compared to the 2 million, well, actually, we're doing okay for ourselves. 95% of values are beneath it. So let's do some examples and see how we can use percentiles. And move over here. There we go. It's a little better. Example 1. The following speeds of motorists in miles per hour were obtained by a highway patrol officer on duty for 2 different weekends. So here's my data. Weekend 1 over here, weekend 2. And if you copy and paste that, or maybe you just type it, you can put it into a single column for each weekend. So what we want to do is find percentiles. I'll do the first one by hand, and then we'll type the next one. I want to find the 50th percentile of the first week on a weekend here. Solution. So for the 50th percentile, if we're looking at what K would be equal to, then you can write 0.5, or you can write that as 50%. That's the percentile I'm interested in. So if we look over at our formula sheet that we just talked about, we should write equals here, percentile. And again, there's different kinds. We're going to do .INC for inclusive, and then it wants to know what cell reference we're going to pull from. Again, the reference is cell : cell, or if you're in Excel, it'll say array. For that first data set, here we are. I want all of these data points over here on the right side. And so if I had to write that in Excel, I could do so. That would be D2 for my top cell. And then I want to keep going down all the way to D15, and that would give me my cell range. But we can't stop there. That only selects the array that we're interested in. I also need to know what the percentile that I'm interested in pulling. So either you can type, here we go, just 0.5, and that'll give you the 50th percentile. And the number that it will compute, again, notice my data is not in any order. It'll compute it like that. That the 70th percentile is 70. And you can write, if you want to give it some units, miles per hour. So let me write that here. I can write P sub 50 is equal to, this is the 50th percentile. That represents that I have 50% values that are less than that, people going slower, but I also have 50% of values that were more than that are going literally faster than that 70 miles per hour. So that was our first weekend. That's like kind of the middle, right? The line in the sand. Let's look at the second weekend and see how that looked. But this time I'll pull up Excel. Find the 50th percentile of the second weekend and what that looks like. Again, you can type your function here, but let me pull up Excel here. A little work down there. Pull up Excel, and it should be up here in a moment. Here we are. So what I'm going to do for the second weekend is I'm going to copy my second weekend data. There we go. I can just hit Control C, go over here. Let's go all the way over to I, let's say, and paste that in over at I. I can see all my data here. Here's my data. If I want to find the percentile, again, I'll write over here for reference sake, P50 for 50th percentile, and that's going to equal, I'll write percentile, and here's your options again. EXC stands for exclusive, meaning you exclude 0 percentile and 100 percentile. Inclusive, that's one we want. The ranking is something different entirely. A little side note, whenever you see the exclamation mark here, it means that function is technically discontinued, and so eventually will be taken out from Excel. So always try to avoid those if you can. Percentile inclusive. Let me double click it, and it says, hey, what array do you want? I can either just drag my mouse, click and drag, and I'll select it here. That looks like I1 all the way to I15, hit a comma in there, and this wants my K, my percentile. So I'll type in 0.5. You can type in enter, and we should get our answer. I always want to put in a little tick mark and show our work here, but this is our answer. Boop. There it is, 75, and that's our 50th percentile. Let's put it in and see if we can answer the rest of these questions. Boom, there we go. All right, let me fill it in mostly for posterity's sake here. And this P sub 50 for this second weekend was 75 miles per hour. Oof, these looks like they were going a bit faster in the middle, right? That's the middle speed. So 50% slower, 50% faster. So one thing that's interesting, this 50th percentile, and again, I encourage you, think about this, 50% slower and 50% faster, is we can think about, there's actually a different name when we talk about percentiles, the 50th percentile. It's a very special kind, and it relates to one of these. It's a little bonus here. Again, 50 percentile means it's completely physically in the middle of our data. Mean, although it is a good measure of center, it's an arithmetic mean, meaning we add everything up and divide. So that's not quite the perfect middle. In fact, when we talk about a physical middle, here we go. This brings us back. That refers to the median. So actually, these two things are the exact same thing. There's no difference between the median, P sub 50 for the 50th percentile. These two things are exactly the same. Little bonus connection for you. So percentiles are good, but notice there are a lot of them, right? 95 percentile, 50th percentile, but there are some special mile markers that we like quite a bit. And those mile markers are going to be referred to as quartiles. This is an important term for us. Very useful. Quartiles. These are some special mile markers, and they are percentiles, but they're just important mile markers. Excel has a function for you. It looks like this. It's quartiles dot inclusive, just like percentiles, and has the same relative inputs that we put in our cells. But in this time for K, instead of putting in what percentile we're interested in, we're going to put in either 1, 2, or 3, depending on what quartile we want. A little bonus tip for you. You can also type in 0 and 4 for the min and max, but we'll get to that on a later date. So this function will give it to us pretty quickly. So I want to relate a couple, because sometimes this comes up for sure. We have our first quartile, which represents the 25th percentile. We'll see why that's important. Sometimes the first quartile is also called the lower quartile. We have Q2, which we already fondly know as the median. And then we have the third quartile, sometimes called the upper quartile, or QU for short. That represents the 75th percentile. Look, here's the benefit of these quartiles. You see my little graph, my picture here? This represents my smallest data value, and on the right, my largest data value. So you can imagine this is all of my data that we're speaking of. We already know what the median does. The median splits our data in half very nicely. This is the median. This represents a nice halfway point. Well, the beauty of these other quartiles is they're like halfway points for the bottom half of my data and also for the top half of my data. And so it's almost like we're getting a bunch of different medians to speak of. Not only can I tell you where the middle of my data is, but I can tell you, look, for those lower performers, this is their median. And for my top performers, this is my higher median, my lower and my higher performers. And I can tell you a good midpoint for that group. And so again, it's a nice distinction between those two. Look, as a small warning, I want to give you quartile.exe will also give you the wrong answer. Again, this excludes the min and the max, just like the percentile excluding function does as well. So avoid that at all costs. If you're getting the wrong answer, chances are that is the only mistake. Let's do an example computing quartiles. This one, the first one I'll do in Excel. The second one we'll do by hand. The following stem and leaf plot represents the test scores of 26 students in class on a most recent test. Here's a little key. So for instance, if I see 6.1, I know that represents a 61 on the test. Not the best, but certainly we're replacing. So what I want to do is first find the second quartile, Q2, which represents the 50th percentile or the median. Let me bump out of this real quick. So as I look at my data, I can't quite use this. In fact, this is a picture. I can't copy data from this in the format. So we can type it up pretty quickly here. I'll do so. Bum, 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 bum. One of the friendly things about Excel is if you go and you highlight all of your data, you can look down over here. It'll compute an average for you. That's friendly. It'll also give you a count. And so if you're ever concerned, like, hey, did I copy all my data? Well, here's my count, 26 pieces of data. That should be right. 26 students. That's what this data represents. So it looks like we typed them all in. What we want to do, we're actually going to calculate two different quartiles, is I want to calculate Q, or a little sub 2 under there. I want to calculate the second quartile. I can do that. Equals, there's a function for that quartile. Again, make sure you use the inclusive one. So I'll double click it. And then if I click and drag, I can click and drag down. Scroll down a little bit more. There we go. There's all my data. And then I can hit comma on my little list here. Let me scroll up so we can see it. There it is, comma. And then for the second quartile, it says, look, what quartile would you like? 0, the minimum, 1, there it is, 2 for the median. So I can type in 2. Let me copy this over. And there we have what we typed in. So there's my second quartile done and dusted. 76.5 represents the median or the second quartile. Let's bring it back to our notes. Here we go. So that's computing the quartiles in Excel. Again, just for posterity's sake, let's write out exactly what we typed in earlier. And there it is, 76.5. And so I'll just write here that Q2 equal to, all right, for extra bonus points, we'll write the median, and it's going to be 76.5. You can box that. That's exactly the score we're looking for. For the third quartile, again, same function. Let me write capital Q this time, quartile. I want to do dot inclusive again. Same cell reference, H1 all the way to H26. And the input, if I'm looking for the third quartile, should be 3. That's the quartile that we're pulling from. And it looks like that Q3, or another way to think about that, as the 75th percentile, or P sub 75 for our reference. Talk about why later. And I want to write that as 84.25. And I can box that. That's exactly the score we're looking for. The whole benefit of quartiles isn't just a number on its own, but it describes the data for you in a very friendly way. For instance, if I drew my data out, let me draw this over here. It's going to help us out with part C. If I draw my data out, here we go. And certainly I have my smallest score over here at 61. And I have my largest score. If I look, that's a 9 and an 8. That represents 98. But I also have other mile markers that we computed. We had the median, that's smack dab in the middle, somewhere over here at 76.5. I also have the 75th percentile, which is like the middle of the top half of my data. That represents 84.25. But here's how we're going to relate this information. Part C. Say you score 81% on your test. Describe your relative position in the class. And there are kind of 3 different options to speak of. Bottom 75th percentile, top 50th percentile, better than most students. So here's my options, or ways that I can talk about my relative performance. So we have our chart drawn up. Again, this chart is not quartiles. These are actually the scores that people earned. 98 represents the maximum. Here, this score represents the 75th percentile, or the third quartile. 76 again represents the median, and so on. Median, this is Q3, or the 75th percentile. But here we are, right? Oh, it isn't red. Here we are at 81%. That puts us about right here, let's say. This is our 81%. And again, the big question, right? We have to bring this home, let's say, to a parent or maybe to our grandma, and they're like, hey, look, how'd you do on that test? And we can tell them we did an 81, but maybe there's a better way than just giving a random score out. And it goes like this. Bottom 75th percentile, is that true? Well, down over here, this Q3 number, 75th percent. Well, we are in that, isn't it? This is true. Technically speaking, we are in the bottom 70th percentile because we are below the 75% of students. So, okay, what a crummy way to talk about your score, though, to mention you're in a bottom below the 75th percentile. And so a better spin is, in fact, to think about, let's read this one, the top 50th percentile. Here's the 50th percentile. Yep. And are we in that top 50th? Yeah, we are. In fact, so a nice spin, especially better than the bottom 50, is to instead talk about this score, our 81%, we're in the top 50th percentile. Again, I had 50% of students score over here, and the other 50 then scored over here. And 76 is in the middle, 76.5. We're above that, 81. So we scored in the top 50. In fact, it's funny, even a different description rather than talking about the top 50 is we did actually better than most students. Again, if I got a 76.5, I could say I did smack dab in the middle, 50% above and below, but I scored better than that. So that means there's more than 50% of students who scored worse than me. We're doing better than most students. And this is why oftentimes they say in statistics, you can, lies, and damn statistics. There are many ways that you can present information. Either you can present information in, okay, look, technically true, the bottom 75th percentile. What a crummy way to talk. Instead, let's see if we can talk about this information, again, relative performance in a better light. And certainly we can say things like, yes, we scored better than most students. Both of these things are true. One shines a better light on your performance. And so that's exactly what we'll talk about when we talk about position and quartiles. This is an example. It's a bit extra for you if you'd like to pause and read these examples of percentiles and quartiles, but I'll leave it alone for a personal exercise if you'd like. Good. Quartiles have many uses. One of their big uses is to help identify outliers, atypical, crazy values. In order to identify these atypical values, we first need some ingredients. The first ingredient is interquartile range, or IQR for short. IQR for short. Q3 minus Q1, one of the most friendly formulas that you'll get in a statistics class. Q3 minus Q1, that's the third quartile minus the first quartile, or QU minus QL if you want to use the upper and lower language. Here we go. So this is our first ingredient to find an outlier. Look, all an outlier is just an atypical value, right? You got your typical values that you kind of expect, and then all of a sudden you got these crazy values. It's been a while for sure, but if you remember, there was this data set that we considered. This data set we considered where we said it was like 1, 2, 3, 4, and 5 was the nice one. But then it's like we had this really crazy value of 25. And one of the things that did to my data, one of the things it did is if I compute the mean or the average of that data, it was something like 7. It was like way out in the middle of nowhere. So if I lined up my data, 1, 2, 3, 4, and 25, and I calculate the center where most of my data is located, man, I get something completely nonsensical somewhere out here in 7 in La La Land that has nothing to do with most of my data, because that 25 is pulling that mean out there. And so that's why we're very concerned to ask these questions like this 25, is it atypical? Not necessarily to remove it, but just to identify, to say, hey, look, yes, this mean is being shifted unnecessarily because that is an atypical value, and something that we can talk about the data. Here's how we can identify outliers. We first need to establish fences or lines in the sand that we say, look, anything within this barrier is typical. So we have first a lower fence, or LF for short, and it's Q1, that's your lower quartile, minus 1.5 times your interquartile range IQR. Then you have your UF, your upper fence, which is Q3, that's your upper quartile plus 1.5 times IQR. There's actually a really good reason as to why we use these particular formulas, but I want to get into a bit of the nuance here, because you might be asking, hey, look, why 1.5? The short answer is it's a convention. It's something that's often used in statistics. Our book, for instance, our OpenStax book, uses this 1.5 measure, but you might read a different book, again, on a different day, that says 3 for these measures, which would make those fences, again, minus on the low end, adding on the large end, would make those fences a bit wider, meaning that we want a wider tolerance for what we consider typical. And so it depends on the book. It depends on the convention that you're interested in. But 1.5, 3, these are kind of the common measures for fences. So this is the formula for them. Let's see them in practice. How can we identify outliers? Here's our example. The hourly wages for 20 contractors currently employed by a consulting firm are listed below. The manager is suspicious that some contractors are earning an abnormal amount. It is known that Q1 is 23.3 and Q3 is 28.85. Thank goodness somebody did it for us. We're going to round our answers to 2 decimals. Let's get into it. So my first task is I want to calculate the lower fence. And the big question is, does the data have any outliers based on the lower fence? Let's see. If we look at the lower fence formula, I'll abbreviate LF. It should be Q1, that's minus 1.5 times the IQR. Unfortunately for us, we don't have the IQR yet, but we can compute it. If I go back, look at the IQR, the formula is simply Q3 minus Q1. If you'd like, you can type this over here, but let's pretend we're in Excel. I'll do the math inside of here. IQR is equal to Q3, it says up top, is 28.85 minus Q1, you can look up top, is 23.3. And I should get an IQR, in fact, I'll write it over here, equals to 5.55. That is the inner quartile range. So if I go back to my lower fence formula, I have enough space, we'll work it over here. LF is equal to, I have Q1, which is 23.3. I then have minus 1.5. That one stays the same, times the inner quartile range we just found was 5.55. If you do the math, I cheated, I did it beforehand, you should get a number like $14.98. Yep. This is the lower fence. That's part of the answer, right? They wanted to know what the lower fence is. We have it. This is the lower fence. Right, here's me cheating, doing it beforehand. And so the big question is, do we have outliers based on that lower fence? I'd encourage you, again, to think about these like literal fences or barriers. 14.98 exists outside of my data. I'll write LF for lower fence. And the question is, anything outside of here would be considered an outlier or atypical. And it looks like, yeah, nothing outside of my lower fence. We're good in that regard. No outliers to speak of. What about the upper fence? Let me write the formula and then we'll compute it. UF for upper fence is Q3 plus 1.5 times the IQR. Again, I encourage you, if you're struggling with the formulas, you can go back and look at the formula and that will certainly be to your benefit. Q3 up top is 28.85. Then I have plus 1.5 times the IQR we computed earlier, 5.55. If you multiply, then add, again, I did it before and I cheated. Here it is. You get 37.18. And these represent dollar bills for this contractor's rates. So there's my upper fence. The big question is, based on that upper fence, do I have atypical outliers? Again, take that 37, see if you can put it, transpose it onto your data. 37, if I was to draw it, it would be kind of smack dab right here. I'll write UF for upper fence. And again, anything inside of these fences, all these values over here, yep, these are all my typical, these are like, look, everything's normal. These people are getting paid, again, as far as everyone's concerned, normal in the middle. But look at these 2 people over here. There's 2 contractors. These people are getting paid an atypical amount. These are my outliers. And that's what we have out here. So our atypical values are 39.7 and my 43.5. Oops. These are my outliers. They're getting paid an atypical amount. Doesn't mean that we exclude them or cross them off. It just means that we can identify them and say, look, these values are atypical. And that would, if we were to graph, for instance, talk about the mean or the center of data, it would pull my data over and increase the average. So again, maybe these people have more experience than everyone else, an atypical amount of experience. Maybe they do great work and their report cards are amazing. Just depends on the data, but it's something that we can identify is these 2 people get paid an atypical amount. And then we can do something with that data after the fact. Good. We talked about, let me move myself over here. We talked about percentiles and quartiles. These 2 measures are very friendly, especially for the layman. We use them all the time, especially when we're talking about position of data. Although for an academic sense, what we're a lot more interested, especially for complex analysis, is this notion of z-score. This is another measure of position. In fact, really, it's like the second one. The first one being percentiles. And then again, quartiles are just a very special kind of percentile. Z-score is like the second measure of position. This one is based on the mean and standard deviation, and actually has a great display of what it does with data overall. So you have two formulas, kind of, for z-score, and it looks like this. Here's my formula for z. X, referring to my data, minus this character is mu, or we can think about that as the mean, or the average, divided by, and this is technically sigma, or an upside down q. You can refer to that as the standard deviation. So this is the formula. I subtract these two up top, and then divide by the standard deviation, and I'll get a z value, a z-score. If we look at the sample formula, it's actually the exact same. We just have to change our symbols or characters because we're talking about a sample. Here's my mean x bar, here's my standard deviation s, and of course x is always representing data. So kind of two formulas, really one, because the characters change versus parameter population stuff versus statistic sample stuff, and that's what the formula shows. So I want to talk about what this z-score is, because we talk about percentiles, 95th percentile, 50th percentile, these lines in the sand. Z-score is a little different. Let me show you what I mean. So take this data point, $17.32. If you plug it into this formula, let's say, you get a z-score of -2. What I want you to think about is, let me write this, $17.32 is really like equivalent to, let me write a different color like red, -2. That these two values, they're equivalent. They're almost exactly equal. It's like looking through a different lens. You cover up your eyes, you look, okay, they're just different numbers, but they represent the same person or the same observation. A little picture, if I can zoom in over here. Little picture over here, boom, there we are. A little picture on that, if I look over here, this represents a z-score of -2. This is just a frequency distribution, much like a histogram, that here, this is my most observations, and then it wanes off as we go over to the left and to the right. Of course, the most observation, if we have symmetric data, nice data, is the mean, because the mean and the median and the mode, they're all the same if we have perfectly symmetric data here. And if I go to the left, there's my z-score of -2, meaning that I'm literally, if I look, -1 standard deviation, the mean -2 standard deviations, I'm literally 2 standard deviations below the mean. Not a top performer in this case. We are quite a bit below the average. And so the reason why we call z-score a position measure is because certainly I can look at this $17.32, or a better measure is if I can look at -2, then it tells me right away, okay, look, I know you're underperforming. You're underperforming by 2 standard deviations below the mean. Again, it's quite a bit more academic than just the percentiles, because it relates to the mean being the center, and then depending on -1, -2, -3, okay, now we're way on the end of this. Or if we have positive z-score, it represents that we're above the average. And that's what this z-score represents. Another thing we often talk about when we talk about this conversion, that we talk about, this is like the X world to the Z world, is often called standardization, or it's called like a transforming. You're taking one thing, you're manipulating it a little bit, and you got your Z world. Again, think about it like a different lens that you're viewing your values with. I have 2 examples of these z-scores. Let's get into it. Good. Judy scored 87 on her statistics exam and was bragging to her best friend about how well she had done. Judy's stats class had a mean of 80 and a standard deviation of 5. So that's all about Judy. So she scored 87, mean and standard deviation. Her best friend, on the other hand, Ashley, was disappointed because she only scored an 82 on her recent algebra exam. Her class's mean was 73 and a standard deviation of 6. And so again, when we compare Judy 87, Ashley 82, bummer, okay, Judy won out, but did she? Let's see. What I want to do is first calculate the z-score for Judy. Let me change color here to my navy blue. Boom. All right. So if I want to write out the formula, and again, I encourage you to do that first. That way, if you make a silly mistake, it'll become apparent. Z is equal to X minus the mean. In this case, I have mu's, population mean floating around, divided by the standard deviation. So I'll do my little upside down Q over here. I can plug in those values that I know. We're talking about Judy here. And so I looked at her score. 87 is her data point, minus the mean, that should be 80, divided by the standard deviation, which if we look up top should be a nice number, 6. And so like 5. Okay, beauty. You can get a calculator if you'd like, or you can do this one by hand. It should be 7 divided by 5. Now as a decimal, that should be 1.4. This is her z-score. And again, the way I'd encourage you to think about this is Judy got an 87 on her test. That's like the X world that you're living in. But instead, think about equivalently speaking, change to red over here. Equivalently speaking, you have her z-score of 1.4. And these two scores are exactly the same, at least equivalently speaking. This one tells you more though, because it tells you the position. Oh, look, she did better than the mean. The beauty of this z-score, again, because you might say, why does that matter? The beauty of this z-score is I don't need to know the mean, right? Cross out, pretend you don't know the mean is 80. If you tell me the z-score, I know, hey, right away, hey, good job, Judy, you did better than the average. In fact, you did 1.5 almost. Standard deviation's better. Nice. Let's see if we can figure out Ashley's z-score as well. Calculate the standard score z-score of Ashley's 82. I gotta encourage you right at the formula. That's a good place to start. Z is equal to x minus the mean divided by the standard deviation. I can plug in these scores. Ashley got an 82. So I'll write 82 minus her average, 73. Ooh, quite a bit lower. Divided by the standard deviation of 6. We can subtract these two. That should be a nice number like 9 minus 6. If you get a calculator, you want a decimal equivalent, you should end up with 1.5 is Ashley's z-score. So again, relatively speaking for her, an 82 for an x value is exactly the same, or at least it's equivalent to 1.5. That is her z-score. So she did, again, better than the mean. But the big question is, if we're comparing these two scores, Judy's 87, Ashley's 82, it's kind of improper to actually compare their data points or their actual scores, because maybe the statistics exam was easier than the algebra exam. In fact, if we look at the averages, we can almost make this observation that the algebra exam, the average was 73 versus the statistics exam, which we crossed off the score earlier, it's right here, at 80. And so yes, Judy did perform better on her test, but relatively speaking, not really, right? The point difference, because it looks like the statistics on average, everybody performed better. And so maybe these scores are not good to compare. Not to compare. Instead, a much more accurate comparison is say, hey, look, relative to your class, how did you perform? So the big question then is, who outperformed whom when considering the relative difficulty of each student's score? Circle your response. Ashley got a 1.5, again, respectable, better than the mean. Judy, on the other hand, only scored a 1.4, slightly less than. And so relatively speaking to the course, Ashley actually outperformed Judy, although her actual exam number might not represent that. But when you go into the z-score, when you actually dive into the data, relatively speaking, the position, Ashley beat out Judy as far as the classes were concerned. Beautiful. All right, last one. So we can go like we did there, where you have X, your data value, and then you can get into z-score. I want to do the reverse. Giving you a z-score, can you get the X value? A lot of times for these questions, I'll tell you, I'll Google different names and see what comes up. And then if I can pronounce it, I'll do it. So let me try not to abuse this. I think it's a Welsh name. Sharn begins learning and playing chess online. Her dad argues that chess is an old game and technology is a blight on a player's ability to learn and improve. Most chess ranking systems are based on a range of 400 to 2,000, although the FIDE, which is just a national ranking for chess, begins at 1,000. In 1980s, the average professional was ranked at 1,100, and the spread, the standard deviation, was 115. Currently, the average ranking is 1,200, ooh, better, with a spread of 300. Interesting. So we have this old and new mentality. What I want to figure out is I want to find the ranking X of a chess player in the 1980s if their z-score was -1. Again, that means that they're -1 standard deviations below the mean. They're underperforming the average. So these are not the top tier players. This is just kind of the entry level business here. I'd encourage you to start off with the formula. They said something about z-score. So I'll write z is equal to X minus, again, they're talking about population information. So I'll write mu for the mean, divided by the standard deviation. Well, I don't know everything, but let me just write what we know and let's see if we can fill it in. So I have the z-score is -1 equals to, the x I don't know, so I'll just write x as a placeholder for now. The mean, I'll write minus 1100 divided by the standard deviation, which is in light blue, is 115. So this is my equation to solve. All right, time to do a little bit of algebra, a little bit of math. We can do it. I have -1 is equal to x minus 1100 divided by 115. Let me multiply this little guy over here. If I multiply it over, nice one to multiply, I should get -115 is equal to x minus 1100 still. Last step though, let me add that 1100 over, and I should be left with, if you have minus 115 and you add 1100 to it, you should end up with 985 is equal to x. For whatever reason, this method of writing bothers me to have it read from right to left, x equals, and so let me rewrite that real quickly. X is equal to 985. This is the score for those underperformers, for those people who are one standard deviation below the mean. And again, this is like the old ranking. All right, old here, the 1980s. What I want to do, what about the new and improved? Find the ranking X of a chess player nowadays whose Z-score is -1, meaning, excuse me, hit here, meaning they're -1 standard deviations, again, below the mean. These are the underperformers, but not of the 1980s, but of the current year. I think I can do this over here. Let me see if we can write the formula again and plug in those values we know. I'll start off again with Z is equal to X minus the mean divided by the standard deviation. Again, write what you know, and then we can substitute what we have. Little arrow sign here. The same as Z-score. I'm interested in -1, but equals, I don't know the data value. Again, that's what I'm trying to find. X minus the mean, but again, this is for nowadays players, so that should be in green. 1200 divided by the standard deviation is 300. The algebra works the same way, but it's important to show our work here. Let me multiply that that 300 over, multiply. And so we'll get -300, there we go, is equal to X, the data point. This should be minus, 1200. Getting ahead of myself. Minus 1200. Last step to solve, let me add that 1200 over, add it over, and then I should be left with 900 is equal to X, or again, as I prefer to write it, if you can bear with me, X is equal to 900. And this is the score, all right, over here, nowadays. 900. So it looks like a little less. So it's like those people who were underperforming back in the 1980s, they could, quote unquote, like get away with 980. That was what the standard Z-score of -1 was equivalent to. Equals -1. Compared to nowadays, that you can actually, again, position-wise, you can think about this in terms of percentiles, that you can still be in this bracket or this range, again, below average, here's the average, here's where you are, -1, that you can still be in this -1 and be at 900 versus before it looks like you had to actually perform a little better and still be in that same percentile or position, -1. So then here's the application, here's what we can ask, and there's actually, one of the best parts about statistics is there are many different ways to answer a question, so long as you can justify why you think what you think. Just like our early example. I think I'm going to have to get it away though. There we go. And we can read most of the question. It goes like this. It says, what is more difficult? Here we go. Excuse me for moving. Was it more difficult to win a random game of chess in the 1980s versus nowadays? Since a lower ranking holds the same position now versus then, meaning that again, this 900 is a lower position to this 980 ranking wise. And so how can we apply that? Well, there's two different ways that we can talk about these positions, or again, answer this question of, was it more difficult to win a game? Back then, back in the day, right? The dad's like, oh, you don't know how hard it was back in my day. Okay, well, let's see how we can spin this. So there's two perspectives. One is that, look, if we look at the individual, if we hyper-focus on just these one scores, then sort of the answer is, you can't answer no, but I'll get to that. The answer is kind of yes. Because if we look at this, again, the players on a person-by-person basis, it looks like are weaker. Again, X equals 900 is technically speaking a weaker player than X equals 985. And so if you wanted to work your way up the ladder, again, just at the average or maybe where people were at, you'd have to work harder to get all the way up there, 900 versus 985. But individual or hyper-focusing on the individual isn't always the best goal. In fact, let me focus instead on this global perspective. We talked about the beginning about mean and standard deviation, how those described, summarized all of my data. We have these two groups. The first one, here's my mean. This is the center where most of my data is located, like an 1100. But this is the spread. You can think about this measure as how wild is your data. How wild. The actual term for this is the standard deviation. It's like a movement. You can think about how much you have to move in order to get in kind of these standard gates, if you will. And it looks like, again, although, let me see if I can get my hands here right, 1,000, 100, 1,100, 1,100 is the median or the mean. It's in the middle. And the spread, how far you should go out, it looks like is 115. So maybe most people are around here. This 1,100 and the spread, that's how far you had to move out. And it looks like as time progressed for the new people, here they are, the mean increased, meaning the center increased. So let me take my data, bump it up a bit. But that's not all that changed. I didn't just improve those individuals. Instead, what also happened is my spread increased. So now instead of everybody being close knit around the mean, as the mean moved up, so also did the spread as well, meaning now my data is crazy. I got really high scores, and I also have really low scores. That's what gives us, that's why we got this low number here, is because, again, the spread increased so much that, hey, there's a lot of people that are technically way underperforming the mean, or at least their scores are significantly, significantly lower. And so, again, if we focus on individual speaking, well, yeah, I mean, there are a lot of people that were, quote unquote, better. It was much more difficult to be ranked higher. -1, -1. Yeah, more difficult. But if you think about on a global scale, well, yes, we have more people who underperform, but also we have much more people who overperform as well. Again, we can look at, for instance, no, it was not easier to win a game because you can consider, again, the average was greater and more spread. I had more, quote unquote, good players. People were, again, that spread changed. Mean tells you where the center of your data is. And certainly if I just look at the mean, I can say, yeah, these people got better. But what explains that Z value is that not only did the mean go up, but also the spread did as well. And so all the way down here, the minimum score, right, the worst player is certainly much lower than it used to be. And so it's these kind of analyses that we can do, again, individual basis, position, versus a global perspective, mean and standard deviation. Let me wrap with this. So we talked about mean, standard deviation, these descriptive statistics that summarize all of my data. I don't want to look at all those pieces. But in this objective, we talked instead about position, about, look, how does every single piece of data, look at this poor 985, how does that position relate to the rest? There are two big ways to talk about this. It's percentiles and quartiles. It's one way that we talk about position, and also Z-scores. Z-scores is a much more academic one, the one that will continue on throughout the rest of the course, and so it's one that I encourage you to hold on to. Look, let me wrap here. If you enjoyed the video, I appreciate the time you put into it. If you didn't, I apologize. For the rest of us, I'll see you in the next one.